Well, hey, good morning or like afternoon, but yeah. Okay. Yeah, so the plan for today is to just do the solutions. I know, yeah, there's one person in the Zoom, so hello. Maybe there's more people on YouTube. So if you want to ask questions live, please do that on the Zoom. So I posted the Zoom link on the Discord. And then I'll also be checking the Discord. In fact, it's gonna be on my other screen. And I'm gonna do the usual thing, which is just to go through all the questions in the lab. Stop me at any time, especially like if there's not very many people, like it's better if it's like a conversation. Okay. Okay, let me just put the Discord in the other window so that you can look at it. And I'll resize this. Okay. So the first one that we're doing is count the even numbers in the list L. So that should be not very complicated. So we're saying count evens L. And then the idea would be, let's say that L is put it down below so that we can test it right away in the usual way. So the idea would be that if L is something like this, then we have three even numbers, right? So we have 10 and 2 and 16. And the way we would count them is we would go through every element of L and we'll check if it's even. And if it is, then we increase the count by 1. So we start with count equals 0. And then we're saying, let's go through every element of L. So here it's better to use this kind of way of going through L, which is just put the first element in num, and then the second element in num, and then the third element in num, and so on, because we don't really need the location for anything. So this is unlike the example from Friday, where we needed the location of the element in order to do something. For example, if we want to find the minimum of a list and we know to know where it is in the list, we need the location. But here we just need the values. So I'm not going to bother with for I in. I'll instead just say for num in L. And now what I'm going to do is I'm going to check whether the number is even or odd. So even would be num mod 2 is equal to 0. And if it is, that means it's even. So I'll increment count by 1. If it's not, don't need to do anything. And then once I've gone through the entire list L, I'll just return the count. Okay. So that is count evens. So for problem 2, what we're doing is we want to write a list to str, which returns the string representation of the list. So we want the input to be something like this, and we want the output to be something like this. It's a little bit similar to a problem from the previous lab as well. So what are we trying to do here? We're trying to construct a string, right? So if you have a list like this, then the string representation, what we want, right, is we'll start with a string being just, the opening bracket. And then we want to add 10 comma, and then we want to add 2 comma, and then we want to add 3 comma and 7 comma and 16, and then we want to add the closing bracket. Okay, so we want to construct the string this way, if that makes sense. So how to do that. So it's a little bit similar to what we're doing here in the sense that here we're kind of like, we keep incrementing the count. So in the same way here, we'll keep adding stuff to the string, where initially it's going to be just the empty string, and like this maybe, and then we'll keep adding stuff to it. So the simplest thing that you can do, which is like not quite right, but is almost right, is to say for E in L, and then I'm going to say result plus equals, and then we'll just convert the element into the string plus a comma. So we'll say str of E plus comma space. And once we're done with that, we also want to add the closing bracket. And then it's almost there. So let me try to do this. So I'll say return result. We make the list a little bit smaller. And I'll just say, list is whatever, 1, 2, 3. And I'll try to print list to str of that. So here's what that looks like. So this is almost right. So we're printing out 3, but we're printing comma space here as well. So it's probably obvious why that is, but let's go through with it. So I'm stepping in, and here I'm saying, okay, result is for now just the opening bracket. And then E is going to be 1 and 2 and 3. And then I'm converting it to a string so that I can add it to a string, right? Because you cannot say like ABC plus 1, that makes no sense, but you can say ABC plus str1, which is the same as 1 in quotes in this case, which would work. So here we're converting E to something that can be added to the string result, and then we're also adding the comma. So that's going to be like this. So result is now open square bracket 1 comma, and then it's going to become 1, 2. And then it's going to become 3 comma. And now we're going to add the last bracket. And that's the problem, is it's almost there, but we have the comma space. So how to handle it? Well, so this is like a list to string old. So one thing you can do is you can say, well, we need to handle the last element in a different way. So instead of doing this, I'll first convert it to for I in range style of doing things. So that's exactly the same, except now I'm saying for I in range, and I'm adding in the same thing. Just instead of saying E, I'm saying L at I. But now I have the flexibility of saying I actually only want to do it until the last the second to last element. So instead of saying for I in range of length of L, I'll say for I in range of length of L minus 1. So at this point, we just run it to show you what it's going to look like. So we have 1 comma 2 comma and space, and then we haven't added the last element. So now you can say, okay, I want the last element, right? So that means for the tools that we have, that you want to add str of L at length of L minus 1. You can also just say L at minus 1, that would also work. So that's like this. There is only one problem with this, which is that if you try this with an empty list, that would not be good, right? Because if you say L is equal to the empty list, this just crashes. And the reason is that there is no last element here. So, one way to handle it is to just say that if the length of L is 0, I'll just treat it as a special case and return the representation of the empty list right back to the user. So that is now fine, but equally, you do this, that is fine as well, and that returns the nice result. So, okay. So here we have kind of dealing with lists using comparisons. So here we're trying to say, is this guy to this guy? So we want to know whether the two lists are the same or not. List 1, and this is list 2. So how would that work? So if list 1 is like 1, 2, 3, and list 2 is like 1, 2, 4, they're not the same. And the way we would know is, well, those are the same, so we keep checking, and then those are the same, so we keep checking, and then those are not the same, so we say false. On the other hand, those are the same, and the way you know it is if you go through them and compare every element, then you won't find a discrepancy. One quick thing to note is that those two are definitely not the same, and you kind of do compare them by just comparing elements pairwise because there's nothing to compare the 4 to. So what we'll do right away is we'll say, if the lengths are different, there is absolutely no way that the two lists would be the same. So it's going to be, hi, so there's a new person on the Zoom, I think, or maybe it's the same person. Anyway, if you have questions, stop me or kind of post on Discord, or works. So, and you can just unmute yourself. So we're going to say if the length of list 1 is not the same as the length of list 2, then we just return false right away. There is absolutely no way that those lists could be the same. And if you return false, of course, nothing after that matters. So if we're on line 5, that means that we haven't returned false, and the lists are the same length, even though the elements might not be the same. So now what we want to do is we want to go through all of the elements in the two lists, and we want to just compare them one by one. And if we find a discrepancy at any point, we return false. So here I do want to know the location because I'm going through two lists simultaneously. So if I say something like for E in list 1, that would not do because there's no way for me to get at what the corresponding element is in list 2. On the other hand, if I say for I in range length of list 1, then I can access list 1 at a time, and I can access list 2 at a time. And I can say, are they the same or not? So here I'm going to say, if they're not the same, then I found a discrepancy, so I can return false. If they are the same, I don't know yet. So if I got into line 10 and I haven't returned false yet, that means that I've gone through the lists, which are the same length, and I haven't found a discrepancy. So at this point, I would return true. All right. So one thing to note here is there isn't a symmetry here because it said length of list 1, but it never mentioned the length of list 2. But that is fine because the length of list 2, if I am on line 6, is the same as the length of list 1. Because if they're not the same, I've already returned false. So that is lists are the same. So now what I want is list 1 starts with list 2. And here what I want is something a little bit different. So I want to say that if list 1, the elements of it are the same as the elements of list 2 in the beginning, then I want to return true. So that would be something like this. On the other hand, if the elements of list 2 are different from the first 2 elements of list 1, in the case that list 2 is of length 2, then I want to return false. So it's kind of the same structure, except I need to basically check if the first several elements of list 1 are the same as the elements of list 2. So if that is the situation, what I need to do, so I cannot do this anymore, but I know that if list 2 is larger than list 1, then it's definitely not the case that list 1 starts with list 2 because there's just more elements of list 2, so there's no way that the first the elements of list 2 fit into the first elements of list 1. There's more of the elements of list 2. So that's definitely false. So now at this point, list 2 is at most as long as list 1, so that's good. So now what I'm going to do is the same thing, except I'm going to change one thing, which is that I'm going to go up to the length of list 2 instead of the length of list 1. So here the logic is that I want to check every element of list 2, but there are more elements of list 1 potentially. I don't care about them. Otherwise, the logic is exactly the same. So that's the function. Okay. So now what I want to do is I want to do match pattern. So what is that? So this is trying to say, does list 2 appear anywhere inside list 1, right? So it might be that this is like 2 and then 1 and 5. And then list 2 is somewhere in list 1, but not necessarily at position 0. So one way to think about it is to say, well, if list 1 starts with list 2, then you do match the pattern. And then if list 1 starts with list 2, but starting with element 1, then that's also true. And in this case, that is what the situation is. So what I'll do is I'll write a helper function that's like this, but slightly different. So I'm going to say list 1 starts with list 2 at I. Let's say at j rather. And what that's going to do is basically handle this kind of situation where I want to return true if list 1 starting with index 1, if j is equal to 1, matches list 2. So, okay. So what's the check here? Well, I want to know whether there is absolutely no way that list 1 would match with list 2. So that would be the situation if you start at index 3, which also has the value here. 3 here, but to be clear, it's 0, 1, 2, 3. So there's no way to match 1, 5 to that because you'd run out of the bounds of list 1. So the 5 would have to be over here. So that, of course, would not work. Right? So how to change this? So we want to ask, if we start at index j, would list 2 run over? So what we can ask is length of list 1 plus j greater than length of list 1? One way to think about it is if j is 0, then this is the same as before. If j is 1, then we're increasing this, essentially increasing the left-hand side by 1, so that if list 2 were of length that's like over 3 for j equals 1, that wouldn't match. And then the same for j equals 2. The other modification here is that instead of trying to match list 1 at I and list 2 at I see there's one more person in the Zoom, or on top of me, I guess. So stop me at any point if you like. So just unmute yourself and ask questions. So we're saying if list 1 at I is not equal to list 2 at I here, and now we're modifying it by saying I plus j. So if j is equal to 1, then we will start comparing list 1 at 1 to list 2 at 0, because we're adding 1 here where j is equal to 1. So, okay. So that's at j, so that was a helper function. But now we're ready to do match pattern. Because all we need to know is, does list 1 match with list 2 at j equals 0? Does it match at j equals 1? And so on until the end. So I'll say for j in range length, not going to be extremely careful about it because this function is just going to return false if it turns out that list 2 would run over. I'll say if list 1 starts with list 2 at j, then we'll return true. So if at any point there is a match, then there is a match. And then if at no point there was a match, then we'll return false. Okay, so this is not the most efficient way of doing things, but this is the way that, like, I would think of it, I guess, if you start with the logic of lists are the same, and then list 1 starts with list 2, and so on. Now, the reason I say it's not the most efficient thing is, like, you're trying, like, does this match here? Does this match here? Does this match here? Whereas in principle, what you could do is just go through list 1 and try to say, okay, like, did it match? Did it match? Did it match? Did it match? So you can do it. We'll do the other way in class later. So that was kind of the intended way. Okay, so we have problem 6. So duplicates. So return true if list 0 contains at least 2 adjacent elements at the same with the same value. So what we want to say is, if you have something like this, then it's true. On the other hand, if you don't have any duplicates, so it's like, 1, 4, 5 or something, no duplicates that are adjacent, then we return false. So, okay. So how to do that? Well, essentially what we want to do is we want to compare listed 0 at 0 to listed 0 at 1, and listed 0 at 1 to listed 0 at 2, and listed 0 at 2 to listed 0 at 3. So those happen to be equal, so these return true. So that's what they'll do. So there is a small mistake here, which I'll fix in a second. So here, I'm just going to say if list 0 at I is equal to list 0 at I minus 1, then we return true. Otherwise, we'll return false. So the issue here is that when I is 0, you're comparing list 0 at 0 to list 0 at minus 1, which means the last element actually. That's not what you want. So you can fix it by just starting at I equals 1 instead of starting at I equals 0. So that would do it. Okay, so this is the coordinate list. So in part A, what you're asked to do is to estimate the velocity at each position. So here we're saying write a function that estimate the instantaneous velocity at time ti by computing a weighted average of the estimates using coordinate I minus 1 and I plus 1, as well as I minus 2 and I plus 2. So let's do that. So here, this would be just at I, right? So how would we do it? So we would say X, and then we would say at I. And what we want to do essentially is we want to say, okay, so the first estimate would be using X at I minus 1 and X at I plus 1. And here, so before the difference was t between or the time interval, so 0.21 in this case. Here it's 0.2 because the distance between I plus 1 and I minus 1 is 0.2. So that would be like this. And then the other estimate would be using I plus 2 and I minus 2. So here the difference is 0.4. So this would be like this. See, there's more people, so maybe there's people showing up for problems have it. So okay. And now what we'll do is we'll say, okay, like we have one estimate using the difference between I plus 1 and I minus 1, and another estimate using I plus 2 and I minus 2. And, you know, like they're both valid estimates. They might be different. So what we'll do is we'll just return kind of the average between them. One way to do it is to just say half of one plus half the other. So you could also say, okay, I care about estimate A a little bit more and about estimate B a little bit less. So I'll estimate like this. Which one is better? Well, it depends on the situation. Okay, so that is part A. So here I said, like, you have the flexibility. So you could, in principle, say, you know, like, if x at I plus -1 is like not a valid coordinate, that's a problem. Equally, if x at I -1 is that's a problem. So let's kind of deal with this in a kind of semi-neat way. So what I'll do, I'll keep this one and I'll edit it a little bit. So what I'll do is I'll just say, x psi 1. So I'll just kind of change those to variables and then I'll make it so that, or rather, let me make a function. So essentially what I'll do is I'll return 0 if x at I doesn't exist. And return x at I otherwise. So what I'll do is I'll say, okay, so if I is smaller than 0 or I is greater or equal than the length of x, then I return 0. And otherwise, I return x at I. So that's going to be a little bit wordier. That's maybe not the ideal way to do it, but that's one way to do it. So I'll say get added value xi plus 1. And in the same way, I'll say get added value x minus 1. And similarly, I think the easier thing to do is to just copy paste this for 4 minus 2. So now what we're doing with our estimate velocity is we're saying compute this kind of combination of the two estimates. And then the way we get the estimates is the normal way, except if I is too small or too large, then we basically change it to 0. So the idea is that if x is a long vector, don't really care about what happens at the edges anyway, just set the values to 0. You can do something smarter as well. So, okay. So now what I want to do is I want to kind of show that if your measurement is noisy enough, then it's better to do this kind of estimate velocity than to do the simple kind of estimate velocity where you just estimate the instantaneous velocity using this. So another way of putting it is it's better to do something like this than to just do something like this. So how would we go about it? So what I want to do is I want to make some data. And the idea would be that we have the correct answer. So we have, some kind of velocity that actually exists, but it's noisy so that we don't get the exact measurement every time. The easiest thing to do is to make a point that just actually moves at a constant velocity, but you're not exactly you're not exactly measuring it correctly every time. Okay. So so with the tools that you have, we'll just do 10 points. So I'll start. So we'll do a different way of doing it later on as well. But I'll start with just, you know, let's say this many data points. And then I'll make the actual data points. I'll say I'll start with an initial position. And what I'll do is I'll just have a constant velocity of 1 for 0.1 seconds. So that means that the ideal data would be 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 6. But the actual data would be like 0, 1, 2, 3, 4, 5, 6, but a little bit different from that because you're adding random noise. So if you do random.random, that gets you a number between 0 and 1 every time. So the kind of noise that you want to get is probably sometimes positive, sometimes negative. So one way to do it is to say, well, what's random.random minus 0.5? Well, sometimes that's going to be positive, and sometimes that's going to be negative. Those are coming out positives, but now it's because it's between, instead of being between 0 and 1, it's now going to be between minus 0.5 and 0.5. We can now multiply it by 0.1 so that it's smaller. So now it's going to be a small positive number or a small negative number. And now what we're going to do is make the data. So it's going to be 0, 1, 2, 3, and so on, except it's going to be that plus a little bit of noise. So that's going to be I plus this much. So let me first print it to show you what that could look like. Okay. Instead of printing, rather, I'll say LFI is equal to this much. And then I'll print the entire list. Because it's so big. So that's going to look like this. So it's kind of like 0, 1, 2, 3, 4, 5, but like with a little bit of a noisy component. So now what we can do is we can make this data and we can return the data and we can estimate the velocity. So data is generate data. And then we can estimate the velocity at location, let's say 4. And let me first print it, and then we'll see. Next is done fine. This is data. So the velocity is like something like this. It's a different thing every time. And the ideal velocity is 10 because this is like 1 per 0.1 seconds, so 10 per second. So it's off by a little bit. And now you can imagine that if you play around with those guys, that you would get a better estimate. So how to handle this? Well, what we want to do essentially is we want to say, let's try this multiple times and see on average how far away from 10 do we get. So there's multiple ways of doing it. I'm going to do like the simplest possible thing. So I'll say diff10 is like this. And then, well, like this, I'll do an even simpler thing. So sum of errors is 0. And then I'll just repeatedly estimate the velocity. So I'll say for I in range, whatever, 10,000. So I'll just try it 10,000 times. I'll say, okay, how different is it from 10? It could be larger, could be smaller. I'll take the absolute value. And I'll add this to sum of errors. So what sum of errors is going to be at the end is the sum of the absolute differences between the estimated velocity and the actual velocity, which is 10 every time. And then I'll print, let's say, the sum of errors. So that's going to be like this. If I divide it by the number of the measurements, I'll get kind of a number that's like, what's the average absolute deviation from the estimate? And the answer is 0.104, basically, 5 sometimes. So now kind of the simplest hacky thing that you can do is you can just say, okay, can we show that this is, so the reason it's different every time is we get new random numbers every time, right? But it's consistent, or consistent to some extent. Maybe if we increase it, it's going to become more consistent. So now it's like basically the same thing to 3 significant digits every time. So here I'm replicating this number, which is not great. So just put this here. I'll add another 0 for good measure. And I'll just make those be n. So that's maybe taking a slightly longer amount of time, but now it's even more consistent. So now that I've gotten it to be consistent, what I can do is kind of just to verify that this works, I can say, okay, so this was 0.105 for this kind of thing. And now what happens if I just use 1.0 estimate VA and 0 times estimate VB? And that's quite a bit larger. Just to check that it's consistent, I'll run it several times. Seems consistent. What might be nice to do, and you should, like if you struggled with this, you probably should try to do more. So you could, of course, instead of doing what I did and just run it in Piezo with, like just changing the function, you can have those coefficients be arguments. That's parameters. So let's maybe do it. So say W0, W1. And I'll return W0, let's call it WA, WB. Let's say this is WA, and let's say this is WB. So now here, when I'm saying estimate velocity, I'll give WA and WB. So maybe I'll say 1.0 here and 0 here. And while I'm at it, I'll also do the other estimate. This would be kind of the instantaneous velocity, meaning you're just taking the difference of the closer points. And here, the weighted one would be So something like 0.6 and 0.4. And then we'll do both this guy and this guy. So now we can do the two experiments together. Say which is which. This is more like instantaneous. On this, there's a problem. So required positional arguments. So this is on here. Okay, so the -10 should actually be estimate velocity, and this is -10. And then similarly here, this is here. And now we get, again, that the average absolute deviation is 0.17 for just xi plus 1 minus x minus 1. But for the weighted, you get a better estimate. So that's about it. If there's any questions, happy to take them up right now. Yeah, Sophia. Yeah.
Sir, I just had a question kind of unrelated to this, but
Okay.
related to the Hopfield nets that we did
Yeah.
yesterday, the day
Yeah.
before. Um, in like the circles, you said how it could only be like -1, 0, or 1. And
Mhm.
like I was just wondering like why.
Yeah. So you mean like why couldn't it be like continuous, right?
Yeah, like why can't it be like I understand the
Yeah.
weight, like how the
Yeah.
weight can be
Yeah.
like it.
Yeah. Yeah.
I don't
And
get
the answer is basically you could imagine making it be continuous. And in fact, there are models where it is continuous. But so the basic problem is with the small nets that we saw, there is a way to just try every possibility and find the minimum that way. But in a larger net, like we said at the very end of the lecture, that's not a possibility, right? So Hopfeld had an algorithm for figuring out reasonably quickly what a relatively good minimum would be without exhaustively searching over all the possibilities. But that algorithm actually relied on kind of the values being just discrete. So that's the reason it's like the practicalities of trying to find a minimum.
okay, that makes
But
sense.
yeah, like there are versions of that, and I'm pretty sure about the history there. Like it's definitely true about the specific algorithms, but there are kind of variants of this where it is continuous. In that particular case, like that's just how it's set up. So in general, with those kinds of things, there are all sorts of just practical constraints in terms of actually being able to make it work. And like so kind of the achievement is kind of both figuring out that you can do it at all, but then also kind of figuring out the practicalities of what kind of how exactly to set up the model so that it actually does something useful. And kind of Hopfield, kind of what we saw in class is just the model and not actually the algorithm that in practice was used to find the minimum, because kind of the algorithm that I showed, that's like the simplest possible one, but not something that would actually scale to larger nets.
Okay, thank you, sir.
Yeah.
And would we ever have to like the weight is gonna like be given to us always, right? Like we won't ever have to try to like find it.
Um, so in the same way that you could, so I mean, the answer is I didn't tell you how to find the weights. And you're right that searching for weights that would encode particular data is hard. And so it's like in the slides that I linked, but it wasn't something that's in the lecture. Of course, I would not ask you to like come up on the spot with an algorithm that won the Nobel Prize. That might be unreasonable, even for ANSI. Uh, so I could imagine kind of problem-solving questions that are not just about like kind of what was on the quiz, but those would be like problem-solving questions, like in the same way that I could like ask you, like do something new with the tools that you have. But there's not like any official problems other than what you saw in the quiz, if that makes sense.
Yeah, that makes sense, sir. And what time are you going live tomorrow for the midterm prep?
Same time, so like 1:30.
1:30? Okay. Thank you so much, sir. Have a good day.
Yeah.
Bye bye.
All right. Is there anything else?
Not for me, no.
Yeah.
Thank you so much.
Okay. All
Bye
right.
bye.
Okay. I'll see you
Bye.
tomorrow. Bye.